See, when we discussed the concept of potential energy at that time, we discussed this thing, the capacity of the object to do work by virtue of its position in the force field or by its configuration. That is called potential energy. So now, capacity to do work by virtue of its configuration, that is the potential energy now that we have to discuss. Okay, and by taking the example of a spring, we can easily understand. Now suppose first we take the spring in its normal condition. See, as shown in this figure, spring is in its normal condition. It implies that spring is not stretched nor compressed. Now see, if from its normal position, so here this normal position, so one end is attached at the rigid support, another end that is attached with a simple object. Now when spring is in normal condition, this particular position we say that is x equal to 0. Now suppose the length of the spring is increased by x. So if we stretch the spring, then we know this thing. The restoring force will develop in the spring that will be in the opposite direction. Under the effect of that particular force, spring will try to restore its original position. So spring force developed here that is in opposite direction of this displacement. Now suppose the spring is compressed by x, then again the restoring force will be in the opposite direction. So here spring is compressed, it implies that the displacement is in negative direction, so force is in positive direction. Here spring is extended means the displacement is positive x, so spring force that is in negative direction. So we can observe this thing as well as experiments shows this thing. The spring force that directly proportional to the displacement and is in the opposite direction of displacement. So we can write a spring force proportional to minus x. Here we introduce one proportionality constant k. So we can write Fs equal to minus kx, where k, that is called spring constant, its unit will be Newton per meter. Spring constant, that is nothing but the restoring force developed in the spring per unit change in the length of spring. Okay. Now, if we change the length of the spring, then inside the spring, the restoring force developed in the opposite direction. So, to change the length of the spring, we have to do work against it, and that work done will be stored in it in the form of potential energy. So now let's calculate it. First see, work done by spring force. Now this particular force is depending on x, means as x changes, the force is changing. So this is the case of variable force. So work done by spring force, that we can write integration spring force Fs dx, and 0 to x, limits 0 because initially spring is in normal condition, and then its length is changed by x. Now Fs equal to minus kx. K is constant, so we can write Ws, that is minus k, and integration of x, that is x square by 2, and limits 0 to x. So resultantly we will get minus half kx square. This is the work done by spring force. So we have to do work against this one. So work done by external force, that will be plus half kx square. Clear? And this particular work done will be stored in it in the form of potential energy. Now see, this work done by spring force that we can calculate with the help of the graph of force versus displacement. So here linear proportionality is there between force and x. So graph will be a straight line passing through the origin, because if x equal to 0, force equal to 0. And here minus k represent this thing, the slope is negative, so line that is downward. Now if we find out the area enclosed by this graph with respect to x-axis, then that will give you the work done. So for this triangle, area that is half into this side means height, that is equal to fs, and this base, that is x. So half into fs into x. But fs equal to minus kx. So if we replace this fs by minus kx, then resultantly work done by spring force that comes to minus half kx square. આપણે એ જ અહીંયા ગણીને લાવ્યા હતા, બરોબર? તો આ રીતે પણ ગણી શકાય. Now see here. Suppose the change is made in the length of the spring from x equal to xi to x equal to xf. Then the work done by spring force xi to xf fs dx. એટલે આગળ આપણે 0 to x લીધી લિમિટ્સ, અહીંયા xi to xf લિમિટ લઈએ. ઘણી વખત x1 to x2 પણ લેવાય, બરોબર? અને આન્સર પાછો આપણો એ જ આવશે માઇનસ કે એક્સ સ્ક્વેર બાય 2. પણ હવે લિમિટ્સ 0 to x ની જગ્યાએ આપણી પાસે xi to xf છે. તો first we substitute upper limit, then minus lower. So we can write minus half k xf square minus xi square. So work done by spring force, that is half k xi square minus half k xf square. See, xi and xf initial and final position છે. So again here we can observe this thing, the work done by spring force that depends only on the initial and final position. It does not depend on the path through which the spring moves from initial to final position. It implies that here we can say the spring force that is also conservative force. એટલે આપણે અહીંયા એ પ્રૂવ કર્યું કે સ્પ્રિંગ ફોર્સ ઇઝ કન્ઝર્વેટિવ ફોર્સ. ક્લિયર? હવે કન્ઝર્વેટિવ ફોર્સ માટે force equal to minus dv by dx. તો એ અહીંયા પ્રૂવ થાય છે. Let's check. The potential energy stored in the spring, that is half kx square. See, this work done by external force is stored in it in the form of potential energy. So potential energy is half kx square. Now differentiate this potential energy. So that is dv by dx. So d by dx of v, that is half kx square. Half k constant, differentiation of x square, that is 2x. So we will get k into x. Now multiply both the side by minus 1. So minus dv by dx equal to minus kx, but minus kx, that is fs. So for spring force, the negative of the rate of change of potential energy, that is equal to spring force. So here we proved this thing, spring force is conservative force. That is true, because only for the conservative forces this relationship is true. Clear to all of you?
Yes, sir.
Now we have to discuss how the change in kinetic and potential energy changes for the spring force and the total mechanical energy that remains constant, and we have to plot the graph of these energies versus displacement. Now see, here we already proved this thing. If spring is extended or compressed by x, or we say xm, so that is maximum extension or maximum compression. Then for that maximum displacement plus or minus xm, we can write the potential energy, that is half k xm square. Now total mechanical energy, that is kinetic plus potential. But when maximum extension or compression is given, then at that time spring is steady. So kinetic energy is 0. So that maximum potential energy itself will be the total mechanical energy. But when we release the spring, then what happens? Spring will move towards its equilibrium position. So when spring move towards the equilibrium position or towards its normal condition, then at any point, suppose its velocity is v, and at that point its displacement is x, then we can write at any position of the spring total mechanical energy, that is kinetic plus potential, that is half mv square plus half kx square. But total mechanical energy, that remains same one, constant one. And we proved this thing, that is half kxm square. So half kxm square, that is half mv square plus half kx square. Now here we can understand when x equal to 0. So when the spring is passing through equilibrium position, so at that time this potential energy will be 0. So that maximum potential energy half k xm square, which one was equal to total mechanical energy, is now converted into kinetic energy. So when potential energy becomes 0, at that time kinetic energy becomes maximum, and that maximum speed of the spring when it is passing through x equal to 0, that is given by Vm equal to under root k by m into xm. Now see here, if we want to plot the graphs of these energies versus x, then first take the equations v equal to half kx square and k equal to half mv square. Total mechanical, that is k plus v. So k, that is E minus V, but E, that is half kx maximum square minus half kx square. Now see, first we think about total mechanical. So minus xm to plus xm. Total mechanical energy E, that is half kxm square, that remains the same one. So the graph of total energy versus displacement, that will be a straight line parallel to the displacement, means x-axis. So that remains constant from minus xm to plus xm. Now v equal to half kx square. So at x equal to 0, potential energy is 0. At x equal to xm, potential energy, that is half k xm square, so that will be equal to E. So at x equal to xm, potential energy equal to E. Similarly, at x equal to minus xm, potential energy is equal to E. So graph of Potential energy versus X will be like this, parabolic one. Similarly, now for kinetic energy. Now see, kinetic energy, that is half k xm square minus half k x square. Now in this equation, if you substitute x equal to 0, so if you substitute x equal to 0, then kinetic energy equal to half k xm square. But half k xm square, that is E. So at x equal to 0, your kinetic energy is maximum, and that is equal to E. Now at x equal to xm, so here if we substitute x equal to xm, then half k xm square minus half k xm square, 0. So here at x equal to plus xm, kinetic energy is 0. Similarly, at minus xm also 0. So the graph of kinetic energy, that is this one, this blue one. Clear to all of you? So now here what happens? See the situation. Suppose spring is tied from one end at this rigid support. Okay. And then here, this one is its normal condition. Here we attach a block. Now suppose the block is stretched like this, is displaced like this. Now this maximum displacement, that is xm. Okay. Now at present it is steady. So potential energy itself is the total energy. અને એ આજે આપણે પહેલું ઇક્વેશન લખ્યું ને એ થયું આ. હવે અહીંથી હું ધારો કે આને રિલીઝ કરી દઉં તો આ શું થશે? આમ જશે. પણ ઇક્વિલિબ્રિયમ પોઝિશન ઉપર જ્યારે જશે, નોર્મલ પોઝિશન ઉપર જશે એટલે સ્પ્રિંગ ઊભી નહીં રહે. કારણ કે હવે શું થાય છે જુઓ, આ પોટેન્શિયલ એનર્જી મેક્સિમમ હતી ઇક્વલ ટુ ઈ. હવે જેમ જેમ ઇક્વિલિબ્રિયમ પોઝિશનની નજીક જાય એટલે કે એક્સ ડિક્રીઝ થતો જાય, તો પોટેન્શિયલ એનર્જી જુઓ ડિક્રીઝ થાય છે. પણ એટ એક્સ્ટ્રીમ પોઝિશન કાઇનેટિક 0 હતી. હવે જુઓ જેમ પોટેન્શિયલ ડિક્રીઝ થાય છે એમ કાઇનેટિક ઇન્ક્રીઝ થાય છે. જોયું? હવે એક્ઝેક્ટલી ઇક્વિલિબ્રિયમ પોઝિશન ઉપર આવે કે જ્યાંથી આપણે એને ખેંચી ગયા હતા, their velocity is maximum. So under the effect of that maximum velocity, it will be thrown on other side. એટલે હવે બીજી બાજુ એનું મોશન થશે, એટલે એનું કમ્પ્રેશન થશે. એટલે ફરી પાછી કાઇનેટિક એનર્જી ડિક્રીઝ થશે, પોટેન્શિયલ ઇન્ક્રીઝ થશે. પાછું મેક્સિમમ કમ્પ્રેશન થઈ જશે એટલે ફરી પાછી સ્પ્રિંગ ઇક્વિલિબ્રિયમ બાજુ મૂવ થશે. એટલે ઇન શોર્ટ સ્પ્રિંગના તમને ઓસિલેશન્સ મળશે. સ્પ્રિંગ વિલ એક્ઝિક્યુટ oscillatory motion like this, and during this motion kinetic energy will be converted into potential energy, and potential energy will be converted into kinetic energy, but the total energy that will remains constant one. So this will be the situation. Clear to all of you, beta?